Okay, 4 o'clock. Well, 3:59. I'm a minute early. Welcome back to your favorite class. Yes. Okay. Couple announcements. First, homework number 2 is posted. It's on Centroids. It's going to be due next Tuesday. So take a look at that. I did grade homework number 1 and post your grades on Canvas. You guys did quite well. I graded number 5, which was the fiction problem, and there are a couple issues there, but generally pretty good. I sent you an individual email with some comments back, so your grade should have been in that email, and what you see on Canvas should reflect that. So make sure that that's all good, and if not, send me an email and we'll fix it. Also, simulation number 1, which is kind of the first simulation assignment for this class, is going to be due next Thursday. So that's going to be sort of partially by hand and partially in MATLAB. Make sure you get it going on that. It's on friction, so you have all the tools at your disposal already to execute. It's a pretty straightforward kind of problem. A guy just hoisting a crate on a flat ground. It's a pretty simple problem, but we're analyzing it with some depth. So go ahead and take a look at that and make some pretty graphs and send them to me and etc. All right, I'm pretty specific about what I'm asking for in that simulation, so make sure to follow through on that. Okay, cows in Greece go mew, they don't go moo. Okay, kind of funny, especially since we were talking about friction and yeah, okay. All right, there you go. All right, let's talk about where we were last time. Last time we were talking about centroids, and I sort of introduced this topic on Tuesday, and I was making my way through some of the solutions and doing some double integrals, and I was getting some blank stares. It seemed that people hadn't really seen double integrals yet or were a little bit shaky. And I tossed and turned in my bed that evening, and I thought, well, is there a way that I can sort of get through this with only using single integrals? The answer is I could probably do that, but I'm not going to. And here's why. Because you're engineers, and you shouldn't be afraid of math, all right? You're going to have to use double integrals to solve problems in your engineering classes moving forward. So if you didn't see them now or haven't seen them before, you're going to see them now. You're going to learn it now. I'm going to teach you. All right. You can't be afraid of math moving forward. If you're afraid of math and afraid of learning a new topic in math to solve a problem, you're in the wrong field. All right. You're in the wrong profession. So you got to learn how to use math. You can't be afraid of math anymore. So I'm going to teach you how to do double integrals, and I'm going to sort of expect you to do them on your homeworks. You're going to see my solutions worked out for the homeworks using double integrals. So there you go. So that means that we're going to spend a chunk of the lecture today, probably the first half, talking about double integrals, what they are, how to do them, do some very simple examples, sort of utilizing them and showing them how they're utilized. And then at the end, you can compare me with, if you've already learned double integrals, how I did compared to your math teacher. Or if you learn integrals in the future, double integrals, you can come back to me and tell me how awesome I was compared to your math teacher, right? Right, okay. So the reason we need double integrals is because we were talking about centroids. And I'm going to come back to the example that we were working on. And we're going to have kind of like an addendum for maybe the next hour or so talking about double integrals. All right, so let's do that quickly. And so here we're going to sort of aside. So if you want to like, go to the back of your notebook for this aside or something, maybe that's something you want to do. All right, so here we go, an addendum. Or a supplement maybe. And this is, we're going to put a pause on the example we were looking at last time. And we're going to talk about double integrals. All right, rawr, who's excited? Addendum, double integrals, yes. All right, so we're working on centroids. And remember our equation for centroids. Looks something like this. Our x bar was this areal integral, x dA, over the integral of areal integral on the area dA, okay? And similarly for the location of the centroid in the y direction, this was the integral on the area of the variable y times my differential area over the integral on the area of my differential area. And the reason we want to talk about double integrals is because when we're talking about areal integrals like we see here, this is usually executed with a double integral. And so we're going to work our way through these now and talk about how we kind of execute these mathematically. And I'm going to start at a place where we're all hopefully somewhat comfortable, and that's single integrals from calculus. And, you know, suspicious whether or not we're comfortable there. Hopefully we're comfortable there. All right. So let's go back to a place where we're sort of comfortable. And we'll sort of build from the ground up, and assuming that we kind of have the ins and outs of single integrals on our way. So let's look at an example here. Let's say that we have some graph, x, y space, and we have a couple of functions. Let's call them function 1 and function 2, like thing 1 and thing 2. Okay, here's function 1, here's function 2. Let's call this function 1. Whoa. What is going on? So here, this is function 1 of x, and we'll call this guy function 2 of x. All right, so it's like y equals some function of x. All right, and we're interested in, let's say, some area of this particular region here that exists between these two functions. Let's say I'm interested in this particular area here. All right, I want to know what is the area here. And to sort of establish what is the area in this region, I'm going to need some bounds on the x-axis. We know this to be like between like x equals a and x equals b. All right. So if I want to determine the area between these two functions on the domain x equals a to x equals b, you can do this using your single integration from calculus, hopefully pretty trivially. At this point, you've probably had enough experience. So if I want area A, then I can do this with single integration. As the following. My area in this region is the integral from sort of the left side of my domain to the right side of my domain, which is x equals a, to x equals b, right? Of sort of the top function minus the bottom function integrated over dx, right? So this would be like f1 of x minus f2 of x, some other function of x, integrated over dx. All right. This is sort of Calc 1 stuff. Hopefully this is a place of comfort for all of us and we're all okay with this. Yes? Okay. Now what's really like going on here when we're executing this sort of integral? And we think about way back to our calculus days and breaking up what's actually happening here. Well, the general idea is that you're making rectangles that generally have like this area. So you're making many rectangles of area dx times, you know, this f1 minus f2. That's sort of what you're doing. And what do I mean by that is, if we go back up to our graph, you're segmenting this domain here into many, many small bits that are of width dx, right? Okay. And what you're doing when you're actually doing that integral is you're adding up all of the rectangles that you're sort of creating in those width dx. You're adding up all those guys, bang, 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 in that integral, right? Okay, so if I want like the area of this particular rectangle, then the area is dx times what I just saw here is f1 of x minus f2 of x. Okay, so hopefully we're sort of comfortable with that. That's like very basic calculus 101. Okay, so I'm adding many of those rectangles over that particular area, and I'm adding all these tiny little bits across a very specific region with very specific bounds. So here are my bounds on the region. Okay, from like x equals a to x equals b. So that's from like this left boundary, x equals a, to the right boundary, x equals b. Okay, very straightforward and very simple. We're all probably good with this. All right. Now, we have to recognize that we're making these like vertical rectangles, okay? So an example rectangle is like this guy here, and he's got width dx, and the height here is my f1 minus f2, my first function minus my second function. We're all okay with that, yes? So this rectangle in of itself is an area, okay? So the question is, could we somehow integrate along what is like this domain, which is up and down, as well, to create what is the area that is represented by that particular rectangle? So let me explain what I mean here. Let's put that into words. So can we find the area of this rectangle by slicing into many differential elements in the y direction and then integrating over the y direction? So that's sort of what I want to look at here, okay? So now we got this rectangle that is like of some height that we know. And if I want to determine like the area of this guy, I could think of segmenting this particular guy into many, many like elements along this vertical direction that have width dy, right? And that would leave me with some square element that is of dimension dx by dy. And if I'm sort of executing in the same way that I execute a single integral across x, I'm going to have some bounds on this particular guy that I'm integrating across, which go from like f2, which is at the bottom, to f1, which is at the top, okay? So let's look at that sort of mathematically then. All right. With a little more detail and maybe some axes on this guy. Here's my rectangle again. And it's of width dx here. At the bottom, my bottom bound is this f2 of x, okay? My top bound here is f1 of x, okay? So I'm going to slice this guy again, like I sort of showed before, with some height dy, and I'm going to integrate across y. Okay, so I'm making here this little guy here, which is an area created, is dA, which is dy times dx. All right. This is a small differential area now that's got width dx and height dy. Okay. So if I want the total area of this little slice, then I have the following. I'm going to integrate now across this like y direction. Area of this rectangular slice. Okay. That would be something like the following. All right. I think about integrating now in the y direction. So I'm going to have some, dy here. On the bounds, on the bottom here, I'm going from this f2 of x, which is like my bottom bound of this particular guy, to the top bound here, which is f1 of x for this particular rectangle, multiplied sort of by the area of the slice that I make. Here we are. So this is kind of essentially what I'm doing here. And let's be very clear about this. This bit here this gives area of rectangular slice. And this is specifically at location dx, right? Of this like one particular slice. And these are my bounds on this particular slice. Okay. So the idea here now is that I've got the area of this one particular slice by adding up all the bits vertically. Now I've assembled that vertical slice, and I want to now add up all those vertical slices. So now I'm going to integrate over x. Right? I've integrated over y to get this full vertical slice. Now I'm going to integrate over x to get the full area. So the final form after adding all rectangles is I'm going to integrate now over that domain a to b. So my internal integral, the first one I'm interested in here, my bounds are y equals f2 of x to the function that's on the top, adding up all of the bits vertically, okay? Then once I've assembled that vertical column, I'm going to add up all of them, all these vertical columns that I've made. I'm going to add them horizontally using my traditional integration, which is like going from x equals a to x equals b, integrating over dx. All right. So here, this is the area of the vertical rectangle. At this like dx location. And then this bit, just sort of like the outer bit here. Do my best to sort of like bring this together. I should have given myself a little more space, but this outer bit here is adding all of the rectangles sort of in this like horizontal fashion. On this particular domain. Okay, so this would be the total area in that particular region. And this is a double integral. We're executing these from inside out. We first do that internal integral, and then we do the external integral. So let's put a bow on this and maybe do another graphical walkthrough what is actually happening here. All right, so let's visualize this one more time. All right. We've got this XY space. We've got some function up here, some function down here. F1 of X and F2 of X. Okay. I'm interested in one very specific region. Maybe I'll make it in blue for clarity. Here. Going from A to B. Okay. I want to look at one particular areal element in that particular region, and that's where I'm going to start. I'm going to start with, let's do it in red, starting with this differential area here. All right. This is dA, which we know is like dy times dx, or you could do dx times dy. It doesn't really matter. They're both one and the same. And then I'm going to integrate vertically first. And the math behind that was the integral from the bottom, which is f2x, to what will be the top of my rectangle, f1x, integrating over the y dimension vertically. Okay. So I'm making I've gone from this, now expanding in this direction and this direction to create my like vertical rectangle. All right, that's like step number one, right? Creating that vertical rectangle. This is like the integration in y, this particular direction, all right? Now I want to take this guy and sort of integrate him left to right, add up all the sort of vertical rectangles that I've created. Now I want to go this way. And so here, this will be like integrating horizontally. And then you end up with the following. The area of this particular region is inside first. Going from y is f2 of x to y is f1 of x. My bounds on my rectangles that I'm making vertically. So this is, again, adding up all the bits vertically together to create that vertical column. And then I'm going to add all those rectangles together on the bounds x equals a to x equals b, where this is a and this is b. And this is like kind of your final form of like this particular double integral. Okay. So that's really what a double integral is. You're starting with this really tiny area that's of area, you know, dx by dy, dy by dx, and you expand to create this vertical column first by integrating over y. It's like this internal integral portion. Then, once you've created your vertical sort of area, you're going to add up all of those rectangles side by side. by integrating over x. So let's do an example quickly. Let's find area. Between the following functions. Y equals 1 plus x squared. And y equals 2x squared. On domain -1 to 1. All right. The graph of this. See if I can do the best that I can here. All right. My bottom guy, which is the 2x squared, is going to look something like this. And my top guy, which is 1 plus x squared, will look something more like this here. All right. Not the best picture. Again, like I said, I'm like the worst Pictionary partner in North America, but there you go. Get the idea. So I'm looking more or less for the area in this region. Now, with your traditional integration, this would be easy. I'm integrating from what is here -1, +1, -1 to 1 of the top function minus the bottom function. That's 1 plus x squared is the top function, minus the bottom function, 2x squared. All of this dx. All right, nothing too difficult about this guy. 1 plus x squared minus 2x squared is 1 minus x squared. So this will be x minus x cubed on 3, evaluated from -1 to 1. And you'll get here an area after executing this of 4/3. All right, so that is your traditional single integration. I just want you to see how the single integration works. You've done this before, so it should be pretty straightforward. Now I want to show how this works with double integration, and you'll see how it whittles down and becomes pretty straightforward. Okay. The idea here is this is an integral on the area of dA. This is how you would see it in practice. Right? I'm adding up all of these differential areas, all of those little squares, across the entire area. All right? That is how you would see it in practice. Here, if we wanted to set this up, I'll do my interior integral first. Give you a second to copy. And let's talk about this. All right. I go to one particular location in this guy. Let's go to this area here. That square. It looks like a smiley face with a janky tooth, right? What's up, guys? And I'm going to move this way to sort of create rectangles. All right. And when I do that, I'm going to create first this vertical rectangle that looks something like this. All right. And we see this vertical rectangle runs into the boundaries, which is on the bottom here, like F2 is equal to 2x squared. That's sort of the boundary it runs into on the bottom when I construct these vertical rectangles. And on the top, it runs into the boundary, which is, we're calling here F1, which is 1 plus x squared. Right? So my interior integral, when I first start adding all of these bits together vertically, I'm bounded by the function on the bottom, which is 2x squared, and my rectangle is bounded on the top by the function 1 plus x squared. Okay, so I'm going from, on the bottom, here, y equals 2x squared, to the top, which is the bound y equals 1 plus x squared. And I'm sort of traversing the y direction. All right, so I'm integrating or adding all of these bits up in the y direction. That's sort of the integral that I'm going to evaluate first. Once I've constructed that vertical rectangle, now I'm going to add them in the horizontal direction. And my bounds on sort of adding all these horizontal slices are just like how you have the bounds with your original calculus, which is like going from x equals -1 to x equals 1 dx. All right. So I'm adding all those vertical rectangles now from the domain -1 to +1. All right, so let's work through this, and we'll, again, work from the inside out. That's how we execute these double integrals. So I'm first going to look at this guy, sort of alone, and consider that integral. I'm going to retain some of the outside bits, but I'm not going to like worry about those yet. So my bounds are still the same, x equals -1 to x equals 1. The integral of dy is just y, right? So after evaluating my integral, I just get y. And I'm evaluating this integral on bounds of 2x squared to 1 plus x squared. And that's the execution of this like interior integral. Okay, so now I just evaluate this interior integral just like I would normally in calculus. I'm going to take this guy, plug it into this particular function. So I'm just going to get 1 plus x squared. I'm going to subtract this guy plugged into that function. So I'll get minus 2x squared. And you'll see an integral here that represents very similarly the integral that we saw for single integration. The top bound minus the bottom bound. Okay, and here is that very first integral that we had, right? But I've just constructed it in a way that shows how double integrals are executed. Okay, so you can work through again and find that your area will still be 4/3. It's the same integral, okay? All right, so that's sort of how we execute. All right, why is this something we need to talk about? Because, yeah, I just showed that you could do it with single integration. It's like easy, okay? Well, sometimes you get funky looking shapes that are not necessarily easy to evaluate using that traditional single integration. And let me give you an example. We remember this differential area, we originally sort of wrote it above as dy times dx, all right? That means that we sort of like integrate vertically first, right? This dy first, I'm going up in the y direction to make my vertical rectangles. Then I sort of take all my vertical rectangles and add them up sideways, right? But remember that this dA also is the same thing as dx dy. All right. Now in this situation, I might want to construct like horizontal rectangles first and then add them all up vertically, right? Why might that be useful? Well, let's show you an example of where it could potentially be useful. Let's say you have some plate, or now you have a couple of different functions. And maybe you have a function that looks like this. Maybe you have a function that looks like this. All right. So let's call this some function here of y. Right. Here now x is a function of y instead of y being a function of x. So for every value of y, there's a unique value of x. Okay, that's what it means to be a function of y. X is a function of y. Similarly, this guy, you could have something like x equals some function of y. So if we're sticking with our nomenclature, let's call this function number 1 and function number 2. And maybe I'm interested in this area here. It would be rather difficult to evaluate that area using a single integration technique, okay? And that's because your functions are given, in terms of y, not in terms of x, as they are traditionally done. So instead of starting with your, differential area dA and constructing vertical rectangles first, and then adding all your vertical rectangles, it might be more convenient to construct horizontal rectangles and then add all of your horizontal rectangles together to figure out what the area is. That's just more or less flipping which way we execute the double integral first, right? So how would this particular integral look? And let's say that we're evaluating between known limits of y, which are like c to d. Right. So first, I want to integrate horizontally. To get these rectangles here. Right. So to do that, I'm going to integrate horizontally. So I'm integrating over dx. And I'm bounded on the left side by this function, and I'm bounded on the right side by this function. All right. So my limits, if I'm sort of adding up over the x direction first, I'm bounded on the left by this f2 of y. And I'm bounded on the right by f1 of y. Okay. Then add rectangles vertically. All right. So we'd end up with our area, this particular region. Again, on the inside, I still have the same sort of horizontal construction of my rectangles, and that's what I'm going to execute first. Adding up horizontally until I hit my bounds of f1y, f2y. Then once I've created all those horizontal rectangles, I add all those together vertically on the domain from y equals c to y equals z dy. So here we've kind of like flipped which way we're sort of building our rectangles first. And this would be another very common method for calculating the area between two different functions. Okay. Cool. That's your double integral primer. And why we need to do this is because we've not even yet discussed what happens when we actually operate on a differential area, okay? We've only really talked about evaluating an area between two functions to now. It's a good demonstration. But remember, we have to be able to operate on our differential areas. That was like the basis of our centroids. We got all these points all over the place, right? And to calculate the moment associated with each point, with each area, we multiplied that differential area by its length away from the axis, which was like an x length or a y length, okay? So we're weighting each one of these areas by some value, which is like x or y. So back to centroids. So we need to operate on our differential areas to calculate centroids. Remember, we had something like x bar was the integral on the area of x times the differential area. And that's what I mean by we need to operate on our differential area, okay? Here I'm operating on my dA, which is like dx dy, with an additional variable x. So I'm operating on each one of those little areas that exists in my piece by some weighting factor, which is its distance away from the y-axis, the x value, okay? This divided by area dA. Okay, so remember these are our centroid equations. So we need to introduce the idea of a double integral in a differential area, a small area that exists that we're going to expand vertically, horizontally, whatever, because I need to talk about operating on that particular area at each location while we're expanding in those various directions, right? So that's what we're going to have to do to accurately calculate our centroid. Let's do an example quick with a very simple analysis. And that is of a triangle, specifically a right triangle. So much better than a wrong triangle. My genius will not be appreciated in my time, I tell you. Okay, so let's think of your traditional graphing setup so that we can be very clear about the picture here with this right triangle. All right. Now let's say I have this triangle that I'm creating. It's a right triangle, 45 degrees, the horizontal. We know that this point here is like the point 1, 1. If this function here, f of x, is just equal to y. Fx, sorry, equal x. Or you might just want to think of it as y equals x is sort of the definition of that particular line. All right. So this line is defined by, obviously, x equal 1. And the line down here that bounds our triangle is the line y equals 0. going to be helpful in sort of like banging home the idea of your rectangles running into boundaries. Okay, what's the area of this triangle without even doing any integration? Anyone? Which is 1/2. All right. So the area after we do our like double integration and stuff better be 1/2. Right. Right. Again, I'm interested in like obviously this area here. Okay. So centroid are given by the following equations. So let's do that denominator first so we get a little bit of practice. All right, let's focus in on that guy first. Comes up in both equations, so let's just do it. We know that the integral of all the differential areal elements over the area better be equal to the total area, so we better get 1/2 when we execute this guy. All right. So our area is the integral on the area dA. It's our general expression. And now we're going to expand this using the double integral techniques that we just talked about. Okay, we could go either direction. We could start with our differential area and then construct vertical rectangles and then add on the domain 0 to 1, or go the other way. So let's talk about this. Here's our differential area dA. It's got width dx, height dy. And maybe we want to construct vertical rectangles here. Calculate this area. So we'll construct vertical rectangles first. That'll be our interior integral on our double integral. So I'm going to sort of first integrate along y. And I'm going to be bounded on the bottom by y equals 0 and bounded on the top by y equals x. Right? So my interior integral, bounded on the bottom by y equals 0, bounded on the top by y equals x. I'm integrating vertically first to make my vertical rectangles. So here we have dy. Okay, I will do this first. It's my vertical rectangles. And then once I've created my sort of vertical rectangles, I'm going to add all those vertical rectangles up along the x direction from x equals 0 to x equals 1. So this is the double integral I'm solving. Okay, baby. Let's dance. All right, integral of dy is just y. I'm evaluating between bounds of 0 and x. X equals 0 to x equals 1 of, if I just plug this in here, it's going to be x minus 0. So let's be explicit about that. X minus 0 after I sort of like plug in using my traditional calculus techniques. The minus 0 is, you know, maybe a little over the top, but I'm just trying to be very meticulous about this. So now when I integrate this guy, I get x squared on 2. Evaluated between 0 and 1, or obviously 1/2. Hey, look at that. Fist pump. Good job, Cole. Fist pump. Rawr. So there you go. It worked. We'll sing the Hallelujah chorus. Hallelujah. All right. That's kind of the easy bit. Now, when I talked about the harder bit and why we actually want to use double integrals in the first place is because we need to operate on those differential areas to calculate our centroids appropriately. So now onwards onto X bar and Y bar. It's the location of my centroid of this particular piece. And if I was thinking about a triangle that looked like this, and it was of uniform thickness and of uniform density, where would I expect the center of gravity of this thing to approximately be? Okay. Well, I would expect it maybe to be somewhere around here. Okay. So I would expect something like this. All right. That's kind of like the location I'm looking for. So that's what I'm looking for right now. What is X bar, Y bar? Okay, we can start with either one. Let's start with Y bar to be spicy. All right, what is the location of Y bar? Well, this is the integral on area of y dA all over the integral A dA. All right, well, I already have this guy here. This is 1/2. So I'm just going to rewrite this as Y bar is 2 times the integral in the area of y dA. I just moved the 1/2 from the bottom to the top. Okay, really the important bit is focusing on this here. All right. This is a double integral. I need to decide whether I'm going to go horizontal or vertical first. Let's maybe just stay with the vertical idea. Okay, so we're going to execute with dA is dy dx. Okay, I'm building vertically first, then adding horizontally. All right. So if I do it that way, let's go with the interior integral first. This is going to look a lot like what we just did for the area integral. We're going to have bounds on the bottom, y equals 0, to bounds on the top, y equals x. And now I need to operate on my differential area. I need to include this y value here in my evaluation of this particular integral. So now this is y dy. This is the interior integral I'm going to execute. I'm still operating on the bounds from x equals 0 to x equals 1 after I've created my vertical rectangles. And this is the double integral I'm working with here. All right. I will do this guy first. Okay, the integral of y dy is y squared on 2. And here I'm evaluating this integral between 0 and x. Right? And we can't forget our dx on the backside. Okay, after I sort of evaluate my integral, this is what I end up with. Okay, so this will be 1/6 times 2, which is 1/3. All right, so the location of the centroid of this particular triangle is 1/3 of the way up the y dimension. All right. So if you've got a triangle that has a height of 1, then the centroid location of that particular triangle is 1/3. If your height is 10, it's 1/3 times 10. All right. It's 1/3 of the way up the height of the triangle. Pretty neato. We'll do the x and then we'll give you guys a break. Again, we know this bottom half here is 1/2. The denominator here is 1/2, so I'm going to rewrite this as 2 times the integral in the area of x dA. And let's do horizontal construction this time. So we'll let dA is dx dy. We'll build our horizontal rectangles first, and then we'll do the vertical rectangles. So if I do it that way, I got to think about constructing this horizontal rectangle first. And this is going to be bound on the left-hand side by x equals y. And it's bounded on the right-hand side by x equal 1. So if I'm making these horizontal rectangles, my lower limit is going to be x equals y. My upper limit is going to be x equal 1. So my integral here will look something like interior first from x equals y to x equals 1. Horizontal construction, x dx, I'm going horizontally first. Y now is going from 0 to 1. Okay, so after I've made my horizontal sort of rectangles, my range is from y equals 0 to y equals 1. All right, now we just execute. All right, so inside here, we're going to have x squared on 2, obviously. Evaluated y to 1. All right, so we'll plug in here. We'll get 1/2 minus y squared on 2 dy. Or finally, x bar 1/2 minus 1/6 is 1/3 times 2 is 2/3. All right. Interesting result. So if we have the triangle that sort of looks like this, and I want to know the location of my centroid, this is that location, 2/3, 1/3. That's the centroid of a right triangle. Okay, I got 4:59 on my clock. Let's take, I don't know, 6 minutes, come back at 5:05. Go do some laps around the building. Go. Rawr. He's got the 1 hour primer on double integrals. How'd I do compared to your math teachers? Okay, good. Okay. Come back and give me an explanation. And tell me how I can improve. Okay, let's get back to where we were. Had a nice 1 hour break there for double integrals. Yes. But now I want to get back to this sort of example problem that we were working on. All right, so back to where we were. We were looking at this particular, spanner, or whatever you want to call this. And I was interested in finding what is the location of the centroid here, x bar, y bar. What is that, location? All right. We had sort of worked our way through this partially. And one thing that we needed as like an interim piece of information is to determine what this constant k was. We just did that with the sort of geometry of this piece, knowing that that point there was the point AH. We could calculate what k was using this particular function and found that k was h on a squared. And we did some initial work on this problem, looking at what was the area of this particular figure. And you can go back in the notes and see that we calculated that the area of this particular guy was HA on 3. We did that with a variety of methods. Your sort of traditional integration where we looked at integrating from the boundary x equals 0 to x equals a with this particular function y equals kx squared. That's probably the easiest way to do it. But I also showed the double integral methods both for dA as dx dy and dy dx. So if you want to refer back and watch that video, which is posted on YouTube, obviously. Otherwise, we will continue and we'll look at actually calculating now these centroidal values. So let's first start with looking at finding x bar. Which we'll remind ourselves is the equation integral x dA on the integral dA. Okay. And so remember that we had this already, and we know that this is going to be equal to HA on 3. And so really, I'm just going to focus on this guy. All right. So let's take the techniques that we just talked about over the last hour, and let's apply them to that particular integral. Integral of x dA with this particular, spanner. Now I can select my dA to either be dx dy or dy dx. I don't know, let's just pick one. So let's just do dx dy. And so that means I'm going to sort of construct horizontal rectangles first. And then add all those horizontal rectangles on this range. Second. All right. So with that in mind, the general bones of this particular guy are going to look like the following. I just got to figure out what to put in for my bounds. All right. First thing I want to consider is if I'm like integrating first over this x coordinate, then what are the things that are bounding x? Right. Well, what's bounding x in this situation? The idea is x is going from something to something else. So what is x going between if I'm making horizontal rectangles? All right, well, let's go back up to our spanner and think about what were happening if we were just had some differential element here, like the differential element dA, and I was expanding and creating horizontal rectangles first. Well, I'm going to be bounded on the left by here. I'm going to be bounded on the right by that particular line there. So let's define what these are in terms of x. Because remember, we want our bounds in terms of x here. So obviously here, this is going to be x's square root y on k. And that's just rearranging that particular function. And then my sort of right-hand boundary for these rectangles is going to be x equals a. So my bounds on this interior portion of the integral, if I select dA as dx dy, is going to be on the bottom root y on k, and on the top x equals a. So on the bottom, x is root y on k, and on the top, x is equal to a. Now, once I've sort of constructed my horizontal rectangles, I'm now going to integrate them over to the domain y, sort of the range y, I guess the more technical math term. And here we're going on the bottom, y equals 0, obviously, to the top of this range, which is y equals h. Right. Again, working from the inside out. Start here. Execute that guy first. If I simplify this down, integrating x dx, it's going to be x squared on 2. Evaluated between root y on k and a. All right, so we can whittle this down. Y equals 0 to y equals h. If I sort of evaluate this, I'm going to have positive a squared on 2 minus root y on k squared divided by 2. So let's look at that. Here we're going to have the evaluation, a squared on 2 minus root y on k on 2, something like that, right? It's evaluating the inside there. Still integrating dy. Can sort of rearrange this and make it a little neater. All right. Square root of y on k squared is just y on k. So this will just be minus y on 2k. Y2k, don't be scared. And you guys weren't even born for Y2K, man. That was like a big thing back in the day. Dang. Man, you guys don't even know about Y2K. Dang, I feel old. My parents had all these like electronics to Radio Shack so they could like have them approved for Y2K. It was like this great. They had to put like all these stickers on our electronics at home that said like Y2K approved. Oh my gosh, it was insane. Okay. Anyway, we can continue. We can actually evaluate this now. A squared y on 2 minus squared on 4k. Evaluated between y equals 0 and h. This will be a squared h on 2 minus h squared on 4k. We sort of let k be h on a squared. And this is going to be a squared h on 2 minus a squared h on 4. Sort of after plugging in for k. And then finally, we get that this integral x dA is just a squared h on 4. All right, cool. Using double integrals. Yes. Exciting stuff. It's not like your math class where you just like learn how to do it and then you have to do it 5,000 times. Like we're actually doing it. It has application. Like imagine that. Okay. So then the centroid, which remember is this integral x dA on your integral dA, is a squared h on 4, all divided by the area which we sort of solved for before, which was HA on 3. If you work this out, the location of your centroid x bar here is 3A on 4. Pretty cool. So it's more or less 3/4 of the way down the domain. Sweet. All right. Do the same for y bar. I'll go through this one a little bit more quickly. Okay. Again, we know dA to be HA on 3. So I'm really just going to focus on like this integral enumerator here, integral y dA. So let's set that up. We can either set dA as dx dy or dy dx. It's a little easier to go dy dx here because we're integrating with respect to y first. Just makes a little bit more sense. So we'll let dA is dy dx. And let's evaluate. Here's our skeleton. Now I got to figure out my bounds. Sort of integrating vertically first. So on the bottom, I'm going to run into the line y equals 0. And if I'm constructing these vertical segments, I'm going to run into the function y equals kx squared on the top. All right. That's my interior integral. And then my exterior integral, where I'm considering adding up all the bits kind of in the x direction. I'm going from x equals 0 to x equals a. Okay. So away we go. This will be y squared on 2. Evaluated between 0 and kx squared. This will be k squared x to the 4th on 2. Sure, I work this guy through. Integrating k squared x to the 5th on 10. Evaluated from 0 to a. Remember, k squared is h on a squared, so let's put that in here directly. That's my k squared. A to the 5th on 10. Complicated. Dang. So once all the dust settles here, you'll get h squared a on 10. And remember, this is the integral y dA. This is not the location of the centroid. This is just the numerator equation. Remember that? Okay, so then all this together, h squared a on 10 in the numerator. And remember, our denominator is HA on 3. So you'll end up with y bar 3h on 10 after all that settles. All right. So for this particular spanner, this particular body, the coordinates of the centroid, x bar, y bar, in terms of a and h, are, for x bar, we had 3a on 4. And for y bar, 3h on 10. And here's your final solution. Remember, our original picture looks something like this. I kind of want to verify, does this sort of like make sense? Yeah, I think it kind of makes sense. The picture is not very accurate, but I think the values make sense. You know, you're 75% of the way towards A for the X coordinate, so maybe that's here. And you're 30% of the way towards the height for the Y coordinate. So maybe this guy is accurate or pretty close. So the centroid's actually more like there. You know, the picture isn't really doing it justice, I guess, but that's where the centroid's actually located. So if you want to try to balance this on your finger with like equal weights all around, that's where you'd want to put your finger. Balance that guy. Okay, so there you go. There's a good example. Okay, let's move on now with lecture material. Going forward. So we just saw here an example of like one particular figure. We saw the example of the triangle. I think it would be silly to ask you to do like direct integration of very simple shapes. And that's because simple shapes like triangles or, you know, some pentagons or whatever, like these, you know, the spandrel like we just did an example of, they're all sort of like well established and well known at this point. All right, so in your textbook and in a variety of resources, most of these centroids of common shapes have been worked out. So most centroids of common shapes have been established. And there are charts for this. There are charts, rawr. I've included one in your notes. So get thee to the canvas and you'll see common centroids. A chart that looks something like this. All right. I wouldn't expect you to copy this down right now. Please don't copy all this down right now. But there are charts that look something like this. All right, so let's take a dive in on like some of these guys. It's a little blurry here, I guess, but for a triangular area with this particular shape, not necessarily a right triangle, but you know, we sort of talked about this and looked at this example. You see that y bar is h on 3. Okay, so 1/3 of the height up the triangle. That's what we saw when we did our triangle example, so that's nice. We've given an area bh on 2. That's also quite nice. Here, this one comes up a lot actually in practice. Like if you're, once you get to your mechanics and materials class, you'll see this quite a bit. There's a quarter circular area or a semicircular area. If you're looking at this particular guy, you have a semicircular area. Obviously, for a semicircle, the x coordinate's right at the origin. So obviously you're at a location of 0 for the x distance to the centroid, but the y distance, which is sort of like this distance here, depends on the radius. and it's 4r on 3 pi. And that comes up a lot, so you might want to commit that one to memory for future classes. 4r on 3 pi. There's some elliptical ones. There's some parabolic ones here, so parabolic. And we just did this guy here. And if you have this parabolic spandrel, your x-coordinate 3a on 4, we just proved that. Your y-coordinate 3h on 10, we just proved that. And the area, ah on 3. So good that we did that. Good general practice, but a lot of these things already exist. There's charts, so, you know, use the charts, dang it. Here's a general spandrel. Y is k x to the n. Ooh, x to the n. Circular sector, etc. All right, so you get the general idea here. You get the point. Is that there are charts that exist that sort of show this information. Let me back up a little bit here. It's hard without like an actual mouse. So here's one that's in the notes. Take a look at that for reference. All right. In your notes, you'll also see that there's some discussion on centroids of wires. I'm passing over that. All right. I'm nixing the discussion of centroids of wires in this class. If you're interested, you can sort of take a look in the notes and look at centroids of wires. It follows a very similar procedure to what we're doing now. Okay. But you won't see any centroids of wires on any tests, on any homeworks, etc. So no centroids of wires. If you need it for reference, come back to this, you know, in the future. But I do have to squeeze in one more topic before we go. And that's the idea of locating centroids of composite bodies. And in terms of a composite body, I don't mean like a glass fiber epoxy, which would be cool, but I more or less mean plates that could basically be described with general shapes all agglomerated together into one shape. So let's talk about that. So composite body centroids. Right. So let's look at sort of a simple example. Assume you have a plate similar to something that looks like this. Looking at it head on, uniform thickness, uniform homogeneity, etc. That might look like this. Do my best sketch here. Okay. And coming down straight here. All right. So what is the centroid of this particular object? I'm not going to give any dimensions on this, but I'll just say, like, what is the centroid of this? Okay. It'd be a pain to kind of think about like defining this line, defining this line, defining this line, all these boundaries. But you notice that you could like cut this guy up into very simple shapes of which we already know the centroid, and maybe somehow add those centroids of those individual shapes together to maybe somehow calculate what is the centroid of this whole object. So can we break this down into simpler objects with known centroids? To help find, let's call it the, you know, composite centroid. And the answer is yes. So let's think about like segregating this guy into like 3 shapes, right? And you see like by my drawing here that we've separated this into like 3 bodies. Maybe let's call this, I don't know, body number 1, body number 2, and body number 3. And that's kind of like what we're working with here. The idea is that each one of those individual bodies, it's pretty easy to establish where the centroid of that guy is, all right? For those triangles, we know that the location of the centroids of those triangles is like 1/3 of the long length in each direction, okay? And we know that the center, or the centroid of that particular square, which is like object number 3, is right in the center, okay? So is there some way that we can work with that to help us establish what is the centroid of this whole structure? That's kind of like what we're after. And the answer is yes. So what we want is pictorially, maybe we try to draw this in 3 dimensions. There's a nice photo in your notes, but here's like X, Y, and Z. And let's think about sketching that guy again. Okay. He's got some thickness. Whoa. Okay. And he has some centroidal location, right? Right. Where we're going to put some equivalent weight, our total weight. How can we somehow we want to equate this to a situation where we've separated this object into kind of those 3 little bits. Okay. Still got some thickness here. Where each one of these individual objects, like this guy has a centroid at that location, this body has a centroid at that location, and this guy has a centroid at that location. And so if we call this, you know, body number 1, this is body number 2, and this is body number 3. Come on. I didn't know if it was showing up like that for me or just for me or for all of you. I don't know why it does this sometimes. A bit annoying. Hey. Hey. Okay, that's body number 3. I guess I can't like draw anymore on this. It's like overwhelmed. Maybe if I just like put it on a new sheet. Okay. Yeah. When all else fails in the engineering world, turn it off, turn it back on. It's kind of like the equivalent of that. All right. So can we somehow execute this where let's call this point here, this is like x tilde 1, y tilde 1. All right. Sort of like this intermediate. Here's x tilde 3 and y tilde 3. Here's x tilde 2 and y tilde 2. Okay. So I want to sort of like do something where I know that these things are equivalent, but how do I do that? Okay. Well, it's going to hinge on kind of like the very first derivation that we did for centroids, where we look at what is the summation of the moments about the individual axes. So we're going to enforce equilibrium, just like we did before. And set like the sum of the moments about the x-axis equal to 0, and the sum of the moments about the y-axis equal to 0. If these things are like in equilibrium, basically the sum of the moments of both of those situations should be equivalent. Yeah, just write sum of moments for both should be equivalent. Must be equal. All right, so that's what we're after. Okay. Well, if that's the case, maybe we look at like sum of the moments about the y-axis equal to 0 first. Sort of on the left-hand side, we have the force, which is the total weight acting at a location of this x bar. And that's going to be equivalent to the weight of object 1 acting at location x tilde 1 plus the weight of object 2 acting at location x tilde 2 plus the weight of object 3 acting at location x tilde 3. Frankly, okay, so if I were to think about that, I didn't really draw the weights in here, but you get the idea. Is that this guy has some weight, this guy has some weight W2, this guy has some weight W3. All right. So the weights of each one of these individual pieces multiplied by their moment arms to those locations of those equivalent weights should be equal to the total weight of the object multiplied by the moment arm to the location of the total weight. That's what we're after. Okay. And since the weight is equal to specific gravity times thickness times the area, and we know, or we're assuming, that these guys are constant. All right, we have constant specific gravity or constant density, however you want to think of it, multiplied by the thickness. We're assuming that the thickness of our plate is consistent, in the z direction. Then we can simplify this more specifically to the total area of the object in the xy plane multiplied by x bar is area of object 1, x tilde 1, plus area object 2, x tilde 2, plus area object 3, x tilde 3. And this is, the situation that we just have here, where it's just, 3 bodies, but we could have 50 bodies. We could have n bodies. All right. So for n bodies, we rearrange. Okay. This is the summation from I equals 1 to n of a I x tilde I, normalized by the total area, but typically we write this to be consistent. I equals 1 to n of a I. This is looking a lot like your general centroid equation, okay? It's because it's derived in the same way, except here we have sort of like discrete entries. So this is for a composite body where you just happen to know like the location of the centroid and of a particular segmented body of your piece and the area of that particular segmented body. And you happen to know them all so that you can sort of like sum the weighted contributions of each of these guys. All right. And we'll say here, same for y bar. Okay, I think we can make it through a quick example. And then you will be free. Find centroid of that guy. Assume, constant thickness and constant density. I'll give you a second to draw. Unless you got the notes in front of you. Oh, how convenient of you. Complicated, dang. How are we gonna break this guy out? Maybe some of you can look at it a little bit and think about it. How do we segment this composite body into like multiple bodies that are easy to identify? I mean, the circle's pretty obvious. But then what do we do after that? All right. Well, I think you could do this a couple of ways. I'll show you the way that I'm going to do it, but you could think about splitting this guy up in a couple of ways. Obviously, the circles here, that's pretty easy to notice, but I'm going to break it up in this way. You've got this object here. I'll call this object number 1. All right. Obviously, I've got this triangle down here. I've got the semicircle that's on the top. I call this number 3. And I have this guy here, circle. And the summation equation that we wrote previously for calculating the centroid of a composite body can be used in a subtractive way, right? So if we think about what the contribution of that particular circle would be and subtract out that contribution, that's, perfectly legit. So here we're going to subtract off that 4th body is the circle. Okay, so I need to establish x tilde I, y tilde I, and AI for all of these objects. I think that's more or less straightforward to do. Obviously, the centroid of the center of this rectangle, if we have here a sort of a width of 120 millimeters, then it's right smack dab in the middle, 60 millimeters. Y tilde, 40 millimeters, halfway up the height of that rectangle. And the area is just the full rectangle, 120 times 80 millimeters. Is going to be 9,600 millimeters squared. Okay. Should be pretty simple to sort of understand that, what's going on with that particular rectangle. All right. Now let's look at the triangle. The triangle, generally, I'm going to be 1/3 of the way along those right dimensions. So I want to go 1/3 of the way down. And so for 2, and 1/3 of the way across, I'm sort of at a location that's here 1/3 of the way across, and I have 120 millimeters in width. So x tilde 1 is 120 by 3, or 40 millimeters. Sorry, this is x tilde 2. Y tilde 2, I'm down here. I have to include the negative here because I'm displaced downwards. My centroid is downwards from the x-axis, so I am going to write this as a negative. And so here, this will be minus 20 millimeters. Right? I'm in the negative y direction to get there. And then the area, object number 2 here is 1/2 base times height. That's 1/2 times 120 times 60. This is going to be 3,600 square millimeters. No, the area is a positive quantity. Right. For object 3, that's this like semicircle on the top. The x centroid of this is pretty easy to establish. It's right in the center. So x tilde 3 is going to be 60 millimeters. Y tilde 3 is a little difficult. So I'm interested in this semicircular shape here, this half circle. And the location of the y centroid of this half circle is a known quantity that we can get in a chart. So if we go to the chart that I sort of lay out in your notes, and I'll just pop that in here for just a second. Here in the chart, you've got this semicircle. And if I want the location of the centroid of the semicircle, what is the y distance? Then the semicircular area, that y height is 4r divided by 3 pi. It's a little bit difficult maybe to see, but it's 4r on 3 pi. So I'm looking at a distance up here to the centroid of that half circle that's 4 times the radius of that guy, 60 millimeters, divided by 3 pi. Okay. But that is not the full distance to get to the centroid of that half circle from the x-axis. I still have to add the height of that 80 millimeters to even begin my journey upwards on the semicircle. So I need to add that 80 millimeters before I even get my journey upwards on this 4r on 3 pi. Okay, so in total, y tilde 3 is 80 millimeters plus 4 times the radius, 60 millimeters divided by 3 pi. You work this out, you'll get the location of the centroid in the y direction for object number 3, which is going to be 105.5 millimeters. The area of object 3, that's just this area of this semicircle, is going to be pi times the radius squared. So pi times 60 millimeters squared divided by 2, because that's a half circle. Area of object 3, 5655 millimeters squared. I'm going to try to bang this out really quick. I know it's been a long couple hours. Object number 4, this is my semicircle. Or sorry, my full circle here, which is this hollow circle. The centroid of the hollow circle is going to be located right at the middle there. So that's at a location of 60 millimeters in x and 80 millimeters in y. So x tilde 4, 60 millimeters in x, y tilde 4, 80 millimeters in y. And the area of object 4, which is pi times the radius of that internal small circle, it's 40 millimeters squared. So the area of object 4 here, 5027 millimeters squared. Okay, so we've established the centroidal locations of each one of those individual objects, and we know the areas of all of those individual objects. So we're finally ready for something like x bar equals the summation x tilde I AI over the summation of AI. Really quickly, I'll just bang through this. All of the different objects, x1 times a1, this is 60 millimeters times a1, which is 9600 millimeters squared, plus object number 2, location of the x centroid is 40 millimeters, multiplied by the area of object 2 is 3600 millimeters squared. Still in the numerator here, sorry, I'm kind of running out of space. Object 3, x centroid is at location 60 millimeters, and the area of object 3 is 5655 millimeters squared. Adding to that the final object, and since this is a hollow inclusion, that circular object is hollow, let's subtract its contribution. So here we're subtracting the contribution from that full circle on the object, and that's at x location 60 millimeters, and has an area of 5027. Okay. All this is divided by, sorry about this, it looks silly. The total summation of the areas, 9600 millimeters squared plus 3600 millimeters squared plus 5655 millimeters squared minus contribution from the circle, 5027 millimeters squared. After punching all that stuff in your calculator, you'll get 54.8 millimeters. You can do the same in the y direction. I'll just give you the answer if you want to work it out. 36.6 millimeters. Okay. Thanks for sticking with on the long lecture today. I don't like going over, but today we just had to bang through the double integral stuff. So thanks for sticking with. Office hours every day, 8 a.m. to 9:30 a.m. Please come and ask questions on this Centroid homework if you got them. I'll try to help you with the double integrals. Please come and ask questions. Have a good weekend, RAR, etc.
You too, King.
Thanks.